So this is the content that we covered last week. So we will proceed from there onwards, and I would like to show you some other diagrams that includes other trace elements also, in addition to the rare earth elements, right? So this type of diagrams we call multi-element diagram. Okay, multi-element diagram means not only rare earth elements, other trace elements are also included. For example, the alkaline elements, large ion lithophile elements, HFSC, high field strength elements. These elements can be there considered collectively, right? So in that case, we call it multi-element diagram. Previously, in the literature, you may have seen frequently, if you read some papers or textbooks, these are called spider diagrams. Okay, but this spider thing does not apply in the recent literature. Instead, we use multi-element diagram, the term multi-element diagram. Okay, so it's a kind of an extension to the rare earth element diagrams, right? So we have a broad more broader perspective than the rare earth element diagram. But in this case, people prefer to use primitive mantle normalization rather than chondrite normalization due to some reasons, which actually that is something to do with the what do you call the differentiation. We don't discuss much on that right now, but just keep in mind, instead of chondrite normalization, people use primitive mantle normalization. Okay, primitive mantle normalization means you can remember the composition of the bulk earth, right? Bulk silicate earth composition. Primitive mantle, that is it, right? Just after core separation, right? Chondrite normalization is just the composition of the chondritic mantle, right? That means before the core separation, what we had was the chondrites, right? So in chondrite, sometimes when the earth was differentiated from chondritic composition, some people believe that some of the trace elements have lost, right? So therefore, people don't want to use this chondrite normalization for the entire set of trace elements when they are presented in multi-element diagrams. Instead, they want to use, they prefer to use, geochemists prefer to use primitive mantle normalization. Okay, so primitive mantle, from the primitive mantle onwards, the later differentiations took place, like continental crustal formation, upper mantle formation, like that. So therefore, assuming all the silicate portion of the earth was starting from the bulk silicate earth composition, people prefer to use this trace element, the multi-element diagrams with the primitive mantle normalization. Okay, but in any case, the incompatibility, the aligning of these elements in the multi-element diagram is in the increasing from right to left. Okay, from right to left. That means the left side will have the highest incompatible elements, right? Irrespective of they are rare earth elements or other types of elements, right? So most compatible elements will be this side, on right hand side. So this arrow indicates the incompatibility increases towards the left hand side, right? In the previous case also we considered the similar thing. Okay, right. And if you see in this case, this is one island alkaline basalt composition from Gulf Islands. It's one of the famous islands for the island, the oceanic island basalts. Okay, so you have the composition like here, and you can see their variation And in this case, we don't see europium. Okay, they don't have included europium there. So that means in that lab, europium was not analyzed, right? It's depending on the analytical capabilities of different machines, right? Sometimes you might not get proper concentration values for each and every element. Okay, but just keep in mind here the pattern, because you need to know how we describe these patterns in general, right? At once you see the pattern, you should be able to describe it uh, as it appears. For example, here the variation is like this, right? So that means uh, the incompatible elements which are lying to your left hand side, that means this way, right? So what is the trend here? This trend means incompatible element enriched pattern. We call it an incompatible element enriched pattern because relative to the compatible elements which are lying in this side, like here, the incompatibles are showing higher compositions, right? Because they are showing higher values. For example, if you take the most compatible element there, the yttrium here, in this case, Y, the element Y, which is relative to the primitive mantle, it's 1, right? It's almost equal to the primitive mantle composition, that means, right? This is not concentration, this is not ppm, remember. Okay, these values are not ppm, this is just a ratio, your sample divided by primitive mantle value, right? So that means your sample, or your your whatever the sample that we are considering, in this case this alkaline basalt from Gulf Islands, right? How high its composition compared to the primitive mantle, that is what you see from the y-axis. You don't see any concentration values, because in geochemistry we are interested in the relative enrichments or relative depletions, not from these diagrams. Okay, so from these diagrams you can't get the absolute values, absolute concentrations. You have to go for the element table, in that case the concentration table. Here we graphically represent how the rock has evolved, whether they have suffered some kind of compatible element kind of issue, or incompatible element issue, right? In this case, we can see clearly the rock has suffered some kind of enrichment in terms of incompatible elements, right? Because you see here the incompatible elements, its composition is like 10 times greater than the compatible elements. While compatible elements are 1, incompatibles are about 10, right? They are about 10. So that means 10 order of magnitude difference. We call it 10 order of magnitudes because if it is 2 times, like here, right, it's 1 order. And if it is 3 times, it's 2 orders of magnitude difference, right? Because this is logarithmic axis, log axis. So how many times? 1 time, 2 times, 3 times, like that comes there. Okay. So this pattern shows incompatible element enriched pattern. Whereas you can further describe this. For example, if you look at carefully, you will see this slight depletion is there. What is that? That's thorium. So you can see in this pattern, thorium is slightly depleted. Relative, this depletion is always relative to the adjoining trace elements, right? That's how you see the depletion or the negative anomaly. This is a slight negative anomaly, not like the previous very strong negative anomaly you saw for the European. Okay, because you see here the difference is large. Difference of the concentrations between the two adjoining elements is large, right? So in that case, you can say it's a strong depletion. That means in your diagram, if you see very strong peak, negative or positive like that, so that means it's a strong depletion or strong enrichment. strong negative or strong positive anomaly. But if you see something like very like this, it's a kind of not very strong or moderate or something like that. Sometimes you might see very slight depletion like this also, right? So these things you have to explain when you describe this type of geochemical patterns, right? And here you can see the samarium, the slight depletion is there, and strontium, very faint depletion is there, right? Lanthanum, slight enrichment is there, right? Something like that, right? Very slight titanium anomaly, very much, very minute, like that. There are such differences observable. So these are important because all these anomalies are result of kind of a geochemical chemical process, because this is a relative composition. And also you remember these are not major elements, these are trace elements. So that means even if a very tiny change of elements or mobility exchange has happened, that is kind of exaggerated in a this type of diagram, because we are using the logarithmic axis as well in addition to this very subtle concentrations. So these depletions or enrichments are very important. So if something is there like depression, that is depletion, and peak like that, positive, that is enrichment. So negative, positive peaks you can see at variable degrees. So these are the normal ways of interpreting geochemical patterns, right? Okay, sorry, I haven't seen this normalization, but in this case also they have used chondrite normalization. Okay, but it is rare for the normal multi-element diagram, right? Because as I said, we use the primitive mantle normalization most of the cases, but it doesn't. I mean, it's not erroneous to use the chondrite composition, but in that case, you are comparing with the chondritic composition, not the primitive mantle composition, right? But it doesn't matter, right? Probably, uh, definitely you will see similar pattern. I mean, almost similar pattern like that, but the relative enrichment or relative depletions might be different, because when you are taking the primitive mantle, the elemental compositions are different. Okay, uh, so this will happen, but the overall pattern might not be changing drastically, right? Uh, because it's a kind of how do you call, it's a kind of parallel type of change you have from chondrite to primitive mantle, right? If you plot those two patterns, primitive mantle and chondrite, together in a multi-element diagram, you will see more or less parallel two curves, uh, but not very much, not very drastic patterns, right? But remember, for multi-element plots, we use the primitive mantle composition rather than chondrite composition. We have another kind of a normalization, because in some cases, a lot of basalts in studies with a lot of basalts, because basalts are produced as partial melting of the upper mantle, right? Most of the cases, mid ocean ridge basalts, mob. And if you deal with such oceanic basalts, most of the cases people also use normalization with mob, because the mob is a product of upper mantle melting, right? So the mob composition, mid ocean ridge basalt composition, most of the cases can be taken as a representative, indirect representative of the mantle also, not not the direct representative, because it is not a mantle composition, direct mantle composition, because it's just a melt formed after mantle melting. But people have used a lot of mobs as a kind of representative composition indicator uh, in an indirect uh, way, indirect manner. Okay, right. So if you plot the ocean island basalts, right? Ocean island basalts. Do you remember ocean island basalts? How they are formed? Ocean island basalts. Mid-ocean ridge basalts are formed at mid-ocean ridges, right? Direct partial melting of the upper mantle. But ocean island basalts, how they are formed? They are formed from the core mantle boundary, very lower part of the mantle, lower mantle, even below, I mean, lower part of the lower mantle, right? Almost the core mantle boundary. That is the plume type of vessels, most of the cases, right? They are coming from very deep, and they have a different composition, characteristically different composition uh, in compared to the normal mob basalts, right? So if you see the composition of the ocean island basalts, it looks like this when normalized to the mid-ocean ridge basalt composition, right? So that means the ocean island basalt composition is divided by mob composition, right? So if you just consider, for example, strontium, let's take strontium, right? So what is the number here? It's almost like 8, 1, 6. It's 6 like. Okay. So that means if mob basalts has 1 ppm composition, ocean island basalts must have 6 ppm. Okay. Right. So obviously it indicates uh, many times higher than the mid-ocean ridge basalts, the composition. And also in this pattern, again, you see kind of pattern like that, trend like that. This means uh, the the incompatible elements are relatively enriched compared to the compatible elements. So that's why you have a steep pattern like that, right? Kind of a steep pattern when you compare those two edges, two sides. So uh, if you plot the mob composition, mid-ocean ridge basalt composition, just in case for comparison, if you wanted to show the composition, where would it be plotted there? If you plot just the mid-ocean ridge basalt composition there, mid-ocean ridge basalt composition divided by mid-ocean ridge basalt composition, right? Mob divided by mob. That means 1. For all the elements, it will be 1, right? Remember we did one example like this last two. Okay. So the mob composition will be like this. This is mob. So how can you compare these elements in this mob with the ocean island basalt composition? You can see the most compatible elements like yttrium, ytterbium, they are depleted in ocean island basalts compared to the mob composition, right? Because they plot below the mob composition. Except those extremely compatible elements, all other elements are enriched compared to the mob composition, right? So that is how the ocean island basalts are different from mid-ocean ridge basalt composition, right? So this is a very important geochemical feature to identify the past geological processes taken place within the Earth's interior. So if you have any mob composition, if your rock, suppose you have a mob rock, right, collected from somewhere, from a mid-ocean region or ocean floor somewhere, right, and you analyze, and it is an unknown sample, right? This is your collected sample. You don't know whether it is mob or OIB or whatever, right? As long as you don't know their trace element patterns or compositions, right? So you have to analyze it geochemically and see what has happened in the history for that rock? What are the geochemical processes? What are the geological influences for that rock? So if you analyze it and suppose you plot that composition and you get a pattern like that, I mean like here, if you get a pattern like this, and another rock, suppose you analyze one more rock, you analyze one more rock and you get a composition like this. Now you have two unknowns. You have two unknown rocks which you have to interpret, right? So what do you think about these two rocks? You have one here and you have, okay, let's say this is one and this is two. Rock number one, what is the pattern? Still you have incompatible element enriched pattern, right? Incompatible element enriched pattern, because uh, we still see this part, this incompatible element part is enriched, right? They are showing a marked increase compared to other sites like compatibles. Their composition is somewhere this level. So what do you think? These two rocks. The number two, what has happened in this case? It has incompatible elements depleted, right? Depleted pattern, incompatible element depleted pattern. So that means what kind of two rocks you have these? You have the mob composition. If it is a mob, if your rock really represents a mob composition, it should be very close to this mob composition, isn't it? Very close to this mob composition, but you are not seeing such close composition because it has deviated above one rock, the other rock below. That means depleted. Okay. So most of the time, this number one, the rock number one, shows significant increase of the incompatibles and also other rare elements also, because you can see the composition somewhere here in here, right? These are also rare elements also included there, which is above, I mean significantly above, because you see here, even this level, it's 2 times, 3 times higher, isn't it? 2, 4, 8, yeah, like that. It goes up the scale, if you see the scale there, log scale, right? So that, but if you think this is an ocean island basalt, what has happened to the composition? If you compare it with the ocean island basalt, actually this is not a representative ocean island basalt, because uh, although this is one representing one ocean island, it is not the exact ocean island basalt composition. Although it says average ocean island basalt composition, I don't agree with that, because here you see there is a marked decrease of highly incompatible elements. So that has that this rock has suffered some other secondary process, I think, in my interpretation, because uh, it it has shown abrupt change here, right? If this is the real average ocean island basalt, this rock should go like this. Okay, this is the normal pattern for the OIB, average ocean island basalts, right? So this is just an ocean island basalt, but from here onwards, okay, no problem. you can take the average composition. So just forget this part for the time being, and consider this average ocean island basalt composition continues like this. Okay, this dark blue line, and compare it with your rock number one. Compare it with your rock number one. Also, it's right hand side. Also, I think there should be some uh, change, because this is again highly depleted. This part is highly depleted. If it is real average ocean island basalt, it should go smoothly like this. Okay, this is how we identify different patterns with global compositions. You will learn it. You will learn it with the time. Okay, right. Anyway, so if you compare this ocean island basalt, and this your unknown rock, suppose you are just comparing it. So several order of magnitude difference is there in terms of this, especially this middle to light, middle to sorry, moderate to what moderate to high incompatible elements. That means this side from here to here, right? Because this is a middle area, so it's like moderate incompatibility. If you had lanthanum like ones, like elements, it should be plotting somewhere here. Okay, it's not shown here, lanthanum, because it's highly incompatible trace rare earth element. So if you compare this average ocean island basalt composition, you can see your rock number one is depleted compared to the ocean island basalt composition, right? So that means it's not it does not represent presently it does not represent the real ocean, I mean a characteristic of an ocean island basalt composition, but it may be an ocean island basalt later interacted with a mid-ocean ridge basalt, right? So this new word you hear now, interaction. What is this interaction? Interaction means it's kind of a reaction. I mean, it's not real reaction, but interaction means it's in variable ways you can have reaction. Multiple reactions can take place between magmas, right? If it is reaction, we have to specify, okay, this CPX plus OPX forms olivine or something like that. But in the case of interaction, we might not be able to derive each and every equation, but of course, you can derive some equations by looking at thin sections by petrological observations. But geochemically, you will be able to explain more clearly, right? This type of interactions. That's why we use interaction, the term interaction in geochemistry, to explain this type of trace or rare earth element variation. Because in the case of a reaction, we normally consider major elements. Remember, for OPX, CPX forming olivine means some exchange of major elements, iron, magnesium, calcium, like those, right? But here we are talking about trace elements and rare earth elements, so we cannot directly relate trace elements to balance any equation, right? They are behaving according to the Goldsmith rule. So you remember the Goldsmith rule. There are three rules of Goldsmith. I mentioned it at the beginning some time ago. Valency and ionic radius, those matters. Okay. So anyway, these interactions can cause original composition to deplete or enriched, to make it depleted or enriched, right? So in this case, your initial composition, probably if this sample was an ocean island basalt, then your sample might have been lying somewhere there, like a pattern, like in this way, right? But later on, it may have reacted. I mean, on the course of in the course of ascent to the shallow levels, because you know ocean island basalts are produced at very deep interior, right? Even comantle boundary. So they should come up, right? They should come up some thousands of kilometers up to reach the mid-ocean ridge levels. Mid-ocean ridge levels means it's very close to us, not very far, like say 40, 50, 100 kilometers, not very far. So, but here you have a lot of melts, lot of mob melts, because the vigorous melting is taking place in the upper mantle region, partial melting, a lot of partial melting. So this type of melts, any drops of melts everywhere present in the upper mantle region, right? Some of these melts are recycling back to the deep mantle levels because the convection forces are acting there. So they can melt and then uh, they can recycle back to the deep interior, right? So when this type of processes are taking place, these upcoming melts from deep interior can be interacted with these shallow melting products, right? So what happens then? Because these shallow melting products must be having lower composition compared to the deep melting OIB like melts, because mob compression is lying here, right? Mob compression is depleted compared to the ocean island basalt composition. So original composition, which was lying here at this level, could have been depleted due to this interaction. Okay, due to this, it's kind of a mixing, right? You are diluting the effect, right? You are kind of dilution. So this type of interaction can happen. Okay, quantitatively we can model these things. That means how much mob melt has contributed to this OIB type uh, melt to produce a present day variation of a value variation like this, right? You can model them geochemically, right? You have to use partition coefficients and many other parameters to do that, which you don't know or need to know right now, but just keep in mind you can do that. Okay, so this type of processes or interactions or some kind of processes can happen, and they can dilute the original composition, because you see in between this OIB and MOB there are no other reservoirs in the earth, right? OIB composition, if it is lying there, and MOB composition is lying in this level, in between there are no recognized earth's reservoirs, right? So whatever the process, later processes should be responsible for patterns between those two compositions. Okay, so this is a very kind of important aspect, because we have to determine this type of variations, and uh, how we can attribute the changes happening to the unknown rock in our geochemical interpretations, right? So this is one objective of this type of studying this type of patterns in trace elements, is very important to study the evolution. Okay, so this is one possibility only, right? There can be so many other possibilities, right? uh, but very general, very simple possibilities. One of those possibilities is here. Okay, and another possibility can be uh, your rock, or the opposite of this can also happen, right? Your rock really represented a depleted composition, right? Your rock represented a depleted composition. Suppose it's like a more like composition somewhere here, right? Originally, but later it was interacted heavily with upcoming this type of OIB type melt. For example, during this recycling, a lot of the mass fraction of the OIB melt is high, because recycling is just maybe some 10%, 20% of the mob melt. Not everything is going back to the mantle again, right? So you have a little portion there, but the OIB portion may be large, okay? So in that case, your interaction will reflect to appear your rock to have high concentration. So that means your sample, your rock original composition has been modified by an enrichment due to an OIB type melt interaction. Okay, because OIB type melt composition is here. It's a very high composition, so it can add uh, to your depleted composition of your sample, and now it can represent a moderately high composition in between these two compositions, right? So in this case, actually, sometimes we call these two as the end, the end members, okay? The end members, because you have one sample here and another sample here. These two interact together and make a kind of intermediate composition. So this is the last end product, right? So these two are the end members, okay? So these type of explanations are there in especially in igneous petrology, and also nowadays it is heavily accommodated with isotopic compositions, because isotopic compositions can also be utilized to understand some of these hidden interactions, because trace elements might not show you uh, real interaction, right? They might be still high. I mean, even though trace elements are very low concentrations, but relative to the isotopic compositions, it is very high composition, right? So there may be areas where we don't see the changes clearly. I mean, the resolution might not be high enough, okay? The resolution might not be high enough. So in that case, you have to use isotopic ratios to check more and more about these minute interactions. Like something like you are using an SCM instead of a petrographical microscope, right? Because in petrographical microscope, you have a limitation, 100 times maximum. You can see the object magnified. But for in between, if something has happened at 200 scale, you can't see that under the petrological microscope, right? So that's why we go for the 10,000 scale with an SCM magnification. So we see beyond 100 there, right? So that is something like that, right? So that's why isotopic ratios are taken heavily in igneous petrology rather than metamorphic petrology. Okay, so this is just one situation where we are using these trace element diagrams in interpretations. Okay, right. So do you have any questions up to now? So you can see the HFS here. What is HFS? It should be HFSC also. Sometimes it's called HFS, high field strength elements, high field strength elements. Actually, all the rare earth elements are also can be categorized into high field strength elements, considering their ionic radius and valency. Okay, but typically we take tantalum, niobium, zirconium, and hafnium as the typical high field strength elements, because they are the mostly used or utilized HFSAs due to their prominent behaviors in trace elements in igneous systems. Okay, but all these elements can be considered as high field strength elements. Okay, including rare earth elements. And the other ones here, you see the large ion lithophile elements. You remember alkaline elements? We call them alkaline elements. They are also called large ion lithophile elements. Sometimes LILE, L-I-L-E, okay, large ion lithophile elements. And they are highly incompatible large and lithophile elements are highly incompatible and they are more mobile, therefore, right? Mobile means they can easily incorporate it into melts. Of course, high field strength elements are also mobile, especially the ones which are lying to the left hand side. Okay, but compared to the large and lithophile elements, high field strength elements are less mobile. They are less mobile. They cannot, they will incorporate into melts easily, but not as rapid as these large and lithophile elements, right? So if you take some compatible elements like these ones, although they are high field strength elements, they do not prefer any melts, right? You can remember this. They prefer solid phases much, right? But it doesn't mean that ytterbium doesn't go into the melt, right? It goes, but it has to choose. If any solid phase is there around, it will fractionate into that, right? Those two should be in equilibrium condition. That means your solid and your melt should be in touch as two phases, right? Then only you can talk about this fractionation. Otherwise, if your solid is here and your melt is here, they are not in touch. You don't see any jumping of ytterbium from here to here, right? Nothing like that, right? They should be in contact, right? They should be in equilibrium condition. Melt, solid phase conditions. Okay, no questions? Okay, right. So we'll go ahead. Then we'll see some of the applications. I think I explained this also last week because their sensitivity of these rare earth elements or trace elements we use in geochemistry, since we can see larger variations, right? For example, this trend changes suddenly like this. Okay, so that means some process has taken place, some geochemical process has taken place somewhere here. Right? But in major elements, you might not see this type of variation. Still, you might see some variation like that. Okay, so identification of the source rock, how these rocks or minerals evolved in partial melting processes or fractional crystallization processes, or even after that. That means post melting or post crystallization, something like we explained here, right? Remember this interaction? Those are post melting processes, right? And also post crystallization processes, right? Those are later processes, right? To understand those also, you can use these trace elements, and we apply it in applied geochemistry. Okay, another important thing when you consider this igneous mineralogy, igneous petrology and melting and all, garnet also plays a big role, right? In mantle, right? Especially in the mantle melting. Like plagioclase before we discussed, it accommodates kind of European anomaly, right? Garnet also causes to concentrate heavy rare earth elements to fractionate into the garnet phase to inside, right, in a rock or a melt, whatever, right? So if the garnet is in equilibrium, so this is what I mentioned here before, they should be in equilibrium condition, right? Whatever the thing, those two phases should be in equilibrium condition. So if garnet is in equilibrium with a partial melt, that means you have a residual uh, uh, phase, residual portion. That means the remaining portion after the partial melting, the solid portion remaining after the partial melting, the melt has escaped like this, but for a certain period of time, this is in equilibrium with this solid here. Okay, before escaping. So if the garnet was there in equilibrium in the partial melt, uh, or even in the residual phase, like in the plateau case before, right? If the garnet is included in the melt, or if it is there in the residual phase, residual solid, right? So it will display you a huge negative slope in heavy rare earth elements. A big negative slope will be shown in rare earth elements. For example, uh, if garnet was there, you will see this type of a big gap, big variation, or even like this, right? So in the previous case, we had seen some light rare earth element enrichment pattern, right? Here, light rare earth element enrichment pattern, like that. Characteristic depletion end can be seen for the compatible elements, right? Not for the incompatible elements, but for the compatible elements, because uh, garnet uh, likes to concentrate compatible elements. That means in this case, heavy rare earth elements are those are compatible elements, right? Heavy rare earth elements, light rare earth elements are incompatible elements. So whatever the compatible phases would like to go into garnet, right? So that the overall rock will show you some depletion like that for the heavy rare earth elements. That happens because of garnet's partition coefficient. You can see the partition coefficient of garnet here. It's greater than 3, right? If something is greater than 1, obviously it is compatible. Okay, so you can see the heavy rare earth elements here. They show big values for the partition coefficient. So that means if this garnet is in equilibrium with with the melt, where these elements are there, most of these heavy rare earth elements will be fractionated preferentially into garnet. Okay. They will be preferentially partitioned into garnet. I think we compared last time these values before, right? So you see very small numbers for other minerals, but for garnet, it's a big number. Okay, so definitely you will see some negative behavior, right? So it's like the europium anomaly you are getting for plagioclase. For garnet, you have this uh, large partition coefficient. So here, for europium in plagioclase, a larger partition coefficient is here, greater than 1, while others are small, except for strontium. Strontium can also go into large contents into plagioclase. But strontium is not a rare earth element. Okay, so similar thing can happen for the garnet bearing rocks also, right? So you can see the both effects, garnet and plagioclase, both effects happening in a rock, right? So in this case, you see the light rare earth elements are heavily enriched there relative to the heavy rare earth elements, right? So that means this rock does not have garnet, right? Something else has happened for this rock, right, to enrich these light rare earth elements. Other elements are almost flat, right? Middle to heavy, they are almost flat. This slight change is not much considerable because other elements can also take up some heavy rare earth element. Therefore, obviously, you will get some slight depletion. That is normal, right? It's not the garnet effect. So you will see the garnet effect, and also you can see the composition there. You see only OPX, CPX, and olivine in the rock. So this is the typical mantle composition, leusolite mantle composition. Remember leusolite composition, olivine 67. You don't need to have these numbers, but you know the triangle, olivine, OPX, CPX, you have, right? Remember the leusolite composition? You have some olivine composition, you have some orthopyroxene, right? And clinopyroxene. So your leusolite composition is lying somewhere here, right? So it's a typical composition. And another rock we have, there you have olivine, OPX, CPX, and plagioclase. Okay. So since plagioclase is there, you see this uh, typical European anomaly. Okay. And another rock you have olivine, OPX, CPX, and garnet. Right. So as soon as garnet appeared, what happens to this slight depletion? It goes down, right? Steeply go down and reflect a pattern like this. Yeah. Okay. Not only there, even starting from the middle earth elements. Okay, just a minute. I have to put the power for the computer. Okay. Yes. So you see the garnet effect. It's very strong, right? Strong depletion. Because the garnet is there in the residue. So this garnet has taken up a lot of heavy earth elements while the melt escaped. Uh, that is what you get as the product as a basalt or something. So in your rock, when you analyze, you will see very depleted pattern for the heavy earth elements because you don't see heavy earth elements in the melt because most of those heavy earth elements are gone into the residue. Or otherwise, this melt has fractionated garnet in the middle of its ascent, this magma. Okay, like it fractionated plagioclase here, right? So if you produce garnet, all the heavies will go into garnet, and the residual or the sorry, the remaining melt. Yeah, you can call it residual melt also, right? The remaining melt will be obviously depleted in heavy earth elements, middle to heavy earth elements. Okay, even middle rare earth elements can be accommodated a lot in garnet. Okay, so this is the pattern that you observe for a uh, for mantle melting when you have this garnet and plagioclase. So this is what we call the garnet and plagioclase effects on effect on not only heavy rare earth. I think we have to cut this edge. Effect on rare earth elements, right? Because europium is not a heavy rare earth element, it's a middle rare earth element. Since you consider both together, did you understand? So different patterns when you see after analysis, you should be able to explain, right? But I think you should have one question now, just by looking at these three diagrams. Can anybody ask me that question? I think at least one of you or few of you should have that question. I mean, you should be curious to see some common aspect for these three rocks, for these three diagrams. හොඳ වෙලාවට මයික් එකක් නැහැ කාගාවත් ළඟනේ. මට කියන්න බැරිුණා ළඟට දීලා යන්න කියලා. So you can get the mic and ask me the question. Just a comparison, nothing else. If your eye and mind is sharp enough to find it, it would be very nice. Can anybody find? අර මේ O level කාලේ ඉගෙන ගත්තා නේද මේ කුලක? අන්න ඒක පොඩ්ඩක් මතක් කරගන්නකෝ. මේ තුනේ බලලා අර මේ මොකක්ද අර අපි ගන්නේ common මේ මොනවාද? මේවා common වුණාම මට මතකත් නැහැ මොකද Venn diagrams ඇඳලා කරන්නේ නේද? හරිද? අර common එක අපි මෙතනට දාන්නේ. ඒ වගේ එහෙම එකක් නැද්ද මෙතන? Don't you have that? Look, in addition to other common things, you have common uh, olivine, OPX, those other things are there, but you should omit these things if you remember the partition coefficient table, right? See, I told you last time, olivine, it cannot accommodate a lot of elements because their partition coefficients are very little. See, OPX also not much, right? It can only accommodate only some selected elements, still small. So therefore, you can just omit. But you see, CPX can accommodate because it's almost zero point 0.5 like here, right? At least these elements and yeah, these ones. Okay, so that's why I was interested in to see this common aspect with respect to the clinopyroxene rather than olivine or OPX, right? Olivine and OPX usually don't have significant fractionation effects in the context of rare earth elements. So that means they cannot take much of them and they cannot affect a lot in geochemical processes. So always remember CPX, garnet, plagioclase, minerals can affect a lot for these geochemical processes. So the other common thing that I expected from you was this and this, right? What is that? It's an enrichment of light rare earth elements, right? Simply, if you commonly explain it, it's an enrichment of light rare earth element. We didn't discuss about that, right? We talked about this europium anomaly. We talked about this flat behavior, and we talked about this depleted behavior, but we didn't talk about this enrichment. I told you that some geochemical process might have happened there, but I didn't explain it, right? Okay, actually this is due to CPX because CPX can take these elements easily. Okay, compared to the other two remaining elements, remaining phases, olivine and OPX, CPX can take up much of these light rare earth elements, right? Therefore, you will see some enrichment in your rock since you have a lot of CPX, right? Like you had garnet in your face. I mean, garnet was they are fractionated, and a lot of trace elements were gone into garnet. So this indicates during the melting, your residual phase contained a lot of CPX also, right? So this lot of the content of CPX here took a lot of light rare earth elements, and the rest of the rock shows this type of enrichment pattern because still they have CPX in abundance there. Here you see 17%. 17% CPX means a large content for the mantle rocks, right? I mean, above 12 or above 15% in general, right? If you have in a mantle rock, that will show you a characteristic feature with relevant to those that particular phase. For example, in this rock, if you had plagioclase more than 15%, this negative anomaly, although it was appeared when you form the rock, might not be there because you have abundant amount of plagioclase in your melt also, so that it will convert into a positive anomaly. Okay, that is also possible. That is another aspect that you have to think of. That means the model percentage of this each and every mineral is also important in melting, right? That means the amount of the phases which, because all these phases were available in your source mantle, right? So it's just a matter of how much of that participate into uh, the melt composition when the melt is formed, right? So huge amount of these phases might be there in the residue, but whereas the some in most of the cases, I mean, some fraction of that will will get into the melt also, obviously. But if that fraction is high, then your rock will show a characteristic pattern uh, for that particular phase. For example, in the residue, the garnet might be very large in this case. But in your melt, if you had garnet, uh, 14, 15 is not enough for garnet, right? Because it's heavy rare earth elements, not like light rare earth elements. If light rare or middle rare earth elements, 15 above 15 is enough to show you a different, I mean, opposite pattern that you are expecting. But if garnet was there more than 20% light, it should be higher. So in that case, your rock might even show you this type of pattern, because the more you include into garnet, I mean, yeah, the more you include into the melt, the garnet composition, the less you see here the depletion. For example, in your melt, if you are enriching garnet little by little, so this pattern will turn into something like this, right? Like this, and then finally maybe like this, right? Because for the melt also, if you are incorporating a lot of garnet during melting, uh, that will bring definitely a large amount of heavy earth elements also, right? But if the melting is taking up only little garnet into the melt, but most of the majority of the garnet is remaining in the residue, then definitely in the melt you will see this type of a depleted pattern. So that you have to keep in mind, because this model amount is also important, not just whether the garnet was present or not. Okay, so if you have a large amount of garnet fractionated in your melt, then your melt even will show you this type of a pattern, positive type of a pattern, because it contains a lot of heavy rare elements. But in the nature, this does not happen frequently. Rarely it happens, but not frequently, because to include a lot of garnet into the melt, it's very difficult, because garnet is an aluminous phase. To melt it and incorporate it into the melt component, it needs a lot of heat, right? So unless there is additional heat within the upper mantle region, you will see only little amount of garnet accommodated in the melt, so that your rock or the basalt or whatever the melt product will show you some depleted pattern, because most of the garnets are in the in the residue. Okay, so this is some deviations from our common explanation. It all depends on uh, the model percentage of these each and every mineral, each and every phase during the melting. So that's why I will show you some modeling examples. You don't have to do modeling, but some geochemical modeling examples later, where we have to consider in equations the model percentage in the melt and model percentage in the residue also, right? So that affects a lot. So in advanced applications in igneous petrology, people use this type of the model percentages of the melt, model percentages of the residue, and fractionation, the partition coefficients, and what the fraction of melt produced, the percentage, what do you call it, the melt fraction, or the degree of melting. All these parameters have to be taken into consideration. Okay. But do you have any question regarding the previous section before we go into the next point? I like if you had some questions. Okay, so let me show you some applications again, where the trace elements as a tool. But in this case, we use the paleotectonic environment to understand the paleotectonic environment. So that it's not, in the previous case, I gave an example for you, something like here, for example, some interactions. That means the petrogenetic implication, right? History of the rock, what has happened geochemically during the formation or after the formation, something like that. Okay, so even here we discussed about some petrogenetic implications, right, in terms of the available phases. But we didn't talk about anything on tectonic settings, right? The tectonic settings means what kind of paleo environment was there when these rocks were originated, right? So these are very useful when we talk about mobile belts. So what are the mobile belts? In metamorphic petrology, most of the cases we talk about mobile belts. So mobile belts are like, for example, Mozambique belt. You remember Gondwana, West Gondwana and East Gondwana collided and formed a huge mobile belt. That is simply an orogenic belt. Okay, it's an orogenic belt uh, as a result of collision. Right? These are mobile belts. We call them mobile belts also. So, because once they are formed in a collision setting, everything is disturbed and you can't find out easily the roots of origins of these different rocks. Because in a mobile belt, although it is metamorphosed now, a lot of rocks available, they are igneous, right? They are igneous, now metamorphosed because of this collision. But during metamorphism, readjustment of minerals has happened, right? So that is what the metamorphism is. So you can't find mostly the igneous traces there. I mean, igneous processes. What has happened? What type of these? What type of rocks these belong to? What kind of setting? Were they representative of ocean islands, or they representative of mid-ocean ridges, or uh, like that, collision of subduction, whatever? You can't find out easily because everything is now in a kind of a melange, mixed zone. A lot of changes has happened, but still, since metamorphism, still we what we recognize it as a uh, closed system behavior, closed system process. Uh, the rocks should be showing some features of their protoliths by geochemistry, right? So that's why we take even metamorphic rocks to find out their protolith information using these trace elements, geochemistry approaches. Okay, so people have tried to find out whether these trace elements can be discriminators of igneous environment. That means the previous igneous environment can be uh, implicated from these trace elements. People have done some experiments and they have found that yes, it is possible. So therefore, we call this is an empirical approach. Actually, what is empirical approach? You have many things: hypothetical approaches, experimental approaches, and empirical approaches. So, what are the hypothetical approaches? So you just assume some, you have some assumptions, and then you build up some hypothesis and do some make some theories or some interpretations based on that. Experimental, you do some experiments and display the exact results and show and maybe describe the process, right? That is experimental. Empirical approach means you don't do exactly an experiment on that, right? And also you are not building up theories, but you use both of those two approaches, the availability of hypothesis and availability of experimental information. You use those two and do some synthesis and present your interpretation. So that is an empirical approach. So that is what we are doing in geochemistry petrology mainly, right? We have already hypotheses, we have already theories, right? And also we have analytical methods, experimental methods, right? We combine them and apply uh, those to our samples and come up with some interpretation. So that is what you call the empirical models, empirical applications, right? So we use the modern occurrences. That means we collect samples from present day, right? We go outside and collect samples and do such kind of a synthesis, right? So we are doing an empirical approach. So doing this, we have to focus on elements that are immobile during low to medium grade metamorphism, because in a lot of tectonic environment interpretations, we are faced with a lot of metamorphic rocks as well, right? So in this low to medium grade metamorphism, we still think all these igneous hypothesis can be applied directly as it is, because it is low grade metamorphism or medium grade metamorphism, where temperatures are not large enough to reset their geochemical behaviors, right? But in the case of granulite phases, it is not medium grade, it is high grade metamorphism. There can be some problems, right? So that's why when we collect samples, especially granulites, we have to be very careful on which part of the rock we are going to analyze for our interpretations. I think I gave you some interpretation or one example using migmatite, right? Migmatite is a granulite phase, extreme granulite phase is rock, right? It's partially melted already. That is the last step of metamorphism, right? After that, if partial melting is also exceeded, then what happens? It will become completely melted. So that means it goes to igneous system, right? No more metamorphism. So that the migmatite means just the initial point of making a magma, right? So not that extreme like rocks, right? But still possible if you collect the correct zones of those samples and concentrate separately each and every layers, felsic zones and mafic zones like that, then it might be also okay. But unless you haven't lost uh, extensive melts during this anatexis, during this partial melting. Okay, so anyway, for low to medium grade rocks, this is okay without any problem, any doubt. Uh, but for granulite phases also we do the same, but maybe we have to put more assumptions in such cases. But anyway, we use these things, these trace element behaviors to understand, to determine paleotectonic environments. Okay, whether it is a subduction zone or whether it is a collision zone or whether it is a rift zone, right? So I think you can remember the differences between subduction, collision, and rifting, right? I'm not going to teach it now, right? You must have learned it by now multiple times, okay, at different levels, from starting from your first years when you study about plate tectonics. Okay, so there are typical diagrams we use to determine the tectonic uh, environments. Actually, these are pre-built diagrams based on, we said, now we are going an empirical approach because these diagrams have used experimental information as well as theoretical information, hypotheses, and everything put together and came up with common observation with global samples, right? So now it has been it has become a kind of a model. I mean, it's very easily applicable for our present day rocks, because we know if any rock present uh, here, uh, for example, if your rock present here, your sample analytical data, for example, here, what is it? Titanium over 100, zirconium, and yttrium. I think here, I can't exactly remember. It's 3 times yttrium over 3. Maybe yttrium over 3, I think. It has missed. So anyway, this type of diagrams are available. These are reference diagrams. So if your rock plots majorly in this region, of course, there can be some deviations due to analytical things, right? And also some due to some other processes. But majority of your rocks are presenting in this blue field. So this WP, WBP, that means your rock is a within plate basalt. Within plate basalt means rifting type basalt, right? It's not a subduction zone, it's not a collision, but it's a intra plate. It's a intraplate tectonic setting, right? So something to do with extensional type of tectonic events, right? Not compression like collision, right? Extensional type. So the geochemistry is different from these different settings. So therefore, you can recognize or distinguish uh, to which tectonic setting your rock belongs to, right? If your rock is plotting here, should be an ocean island basalt, okay, OIB. And if your rock is plotting somewhere here, it must be an island arc basalt. Should be a island arc. So island arc means it's a subduction zone. It should be a subduction zone. So ocean island basalt is not a subduction zone. It's a different thing. It's like more the plume-like basalt. Okay. So if your samples belong to here, it's a more mid-ocean ridge type basalt, right? So likewise, there are several tectonic settings, very frequently spoken type of tectonic settings within plate, island arc. Actually, island arc also you have different compositions. Island arc tholites, island arc basalts, right? Depending on their elemental compositions. But both belong to subduction zone anyway, right? Calcaline basalt, even calcalines are subduction zone, but slightly different from other two, right? Because a lot of calcium is there in those basalts. And ocean island tholites, ocean island alkaline basalts. So likewise, there are a lot of various types of tectonic settings. So I suggest you take one by one each of these tectonic setting and give an explanation uh, for for their definitions and all with example, right? With the diagram, right? And submit it to the Google Classroom, right? That will be another assignment, right? So the description uh, on tectonic settings. You don't have to talk about these triangles or these diagrams. You have to discuss about these settings only. Okay, I'm not asking you to discuss about the diagrams. Only these settings. What kind of I mean, what these samples or these magmas or these melts corresponds to this type of tectonic setting, and what is that tectonic setting? Like that, a brief discussion. Okay. So you submit it to the Google Classroom as an assignment, right? Otherwise, you will never look into these details, right? These are very important if you learn igneous petrology. Okay, so there are different discrimination diagrams because sometimes some diagrams might not give you correct setting due to various reasons. Yeah, practically you will encounter different problems with some of the diagrams. Probably uh, when you get one element or two elements from one lab and another element from another lab, right? Because people do like that, because when they have collaborations, I mean, these analyses are expensive. Okay, so each and every person might not cannot afford to do all the analysis in one lab, so they have to share. So in such cases, for example, if you are supposed to have a plot somewhere here, but you might have it here, right? Due to some differences, analytical problems in the two labs, but it is not recommended anyway for precise interpretations. But people have to do it if nothing is there, no other options, right? If no alternatives are there. But in that case, you can use another diagram to confirm it. Okay, whether it is really ocean island basalt or mid ocean ridge basalt. So extensively, it might plot in this diagram here correctly. So then you can use this diagram also in your interpretations. So it's a matter of usage of which type of diagram. Or otherwise, you can use major elements. So here you have the major elements: phosphorus, manganese, right? Titanium. Titanium both considered as major and trace. Remember, that is also another point that you have to consider. Okay. Sometimes titanium is considered as a trace element, but sometimes it is considered as a major element. It depends all on the availability of phases. For example, if rutile is there a lot in your rock, so there will be a lot of titanium, right? Not only rutile, ilmenite also. So in that case, titanium should represent in your rock as a major element, right? So all depends on the availability of phases. So here, high field strength elements, niobium, right, and sodium combination, alkaline element here, right? Because you need to know from all the angles, right? So if one angle or one triangle differs, so I have to look in another angle using another triangular plot, right? Because here it's an entirely different angle, sodium, alkaline element, I mean, alkali element. Strontium is a subalkaline like type element, large and lithophile element, and niobium is a high field strength element. So three different, entirely different from each other. So your interpretation should be more robust in this in a diagram like this, if you get it well plotted. So this is how the discrimination is taken place. So therefore, we call these diagrams in common discrimination diagrams. Okay, tectonic setting discrimination diagrams. So these are the tectonic setting discrimination diagrams. And nowadays we see these diagrams are applied in metamorphic petrology also, as I said before, to understand the protolith characteristics. We can use them. Not only these 5 diagrams, there are many other uh, very, very common type of diagrams are given here. Showing how these geochemical applications are there. Okay. Okay. So I don't want to go further for today, because the next section is a little bit going deep into partial melting. So you need to be very refreshed for that. So I prefer starting it freshly. But before we start that section next week, you have to be very familiar with what we have already discussed. Okay. Otherwise, you can't remember. If you can't remember the facts that I have told you, you will be in trouble in when we are now to apply them in different occasions. Okay. So even these terms, that's why I asked you to remember compatibility, incompatibility, and those things at least to be very familiar with. Okay, so if you have any question, you can ask now. And don't forget this assignment. I give you another week for that, 1 week for that. So when you come to the next class, you must be very familiar with these tectonic settings. These assignments will be evaluated, okay, as continuous assessments. All right, so if no questions, we can stop here for today. Sign the attendance and submit to the office.